vector space with certain independent directions. These are the basis vectors along those independent directions. So what we have done is a linear combination of the basis vectors. That's what is this one, correct? A vector is found by taking a linear combination of its basis vectors. The components being members of what is called the field. So these can be real numbers or complex numbers in general. But as far as our real vector spaces are concerned, these are real numbers. So we are just taking linear combination of basis vectors to make it. And what is this one here? If you look at together, can I not write it in terms of say that this one corresponds to one basis vector, this corresponds to another, this corresponds to another, etc.? Can we not, sir? This and this are independent of each other. Every one of these 9 things I have written down are independent of each other. Yes? You have to extend your imagination. Okay? They are also orthogonal, of course. They are also orthogonal. I'll tell you the rule. Okay? So, because this says that this is an object having, there is a question of genesis, that is how we arrive at such objects. Is it? Here the idea is that I want to look at two mutually independent set of possibilities, namely the direction of the normal and direction of the force. So I want to construct an object which refers to what the direction of the normal and what the direction of the force are, which means two quantities which we normally think in terms of vectors should be here. So this is what it is. We see that in this case there will be 9 possibilities. So each one of these one are now independent members. That's the first idea that I have. If you think of these 9 elements as independent, the sum is just a linear combination of those 9 elements. So it becomes a vector. Correct? So this is a vector in a certain space. Whenever we talk about a vector, it is in a certain space. That space is called the tensor product space.
So it's a tensor product of what? Product of two?
Product of the vectors that we have considered. So you have 2 vector spaces. I'm taking a tensor product of 2 vectors. Tensor product of 2 vectors.
Tensor product means it is a relationship between 2 vectors?
No, it is saying that we are composing 2 distinctly different things together. They need not even be the same thing. Okay. In general, we can construct tensor product spaces or tensor products involving distinctly different. But I'll come to that shortly.
Is it the same as outer product of 2 vectors?
Yes, it is same as outer product. So this is not the cross product, this is not the dot product, it is a outer product. That is basically we are still having more than one direction associated with each one. So that is the idea that is coming out of this. So viewed this way, the tensor is nothing but a vector, except that the space is now what? The space is now larger than the original vector space, because we are now keeping track of 2 distinctly different quantities simultaneously.
Is this idea very general?
Yeah, it's very general.
Applicable to any tensor?
Yes, yes. Not only this one. Not only this one. You have noted down. Good. The morning I have just anyway. Similar examples will be like type of electric polarizability, magnetic susceptibility. They are all second order. Sometimes you will find third rank. Sometimes you will find objects like this. If you are doing relativity, you will find the tensors having 4 components. I've deliberately put one index before. Morning there was a little bit of discussion about covariant and contravariant. Is it covariant means something transforming like gradient. And contravariant means objects transforming like coordinate system process. Supposing I write an object like this, so this is intended to be, supposing simply I write something like this, okay. This is intended to be components of a vector, just only one component. So this refers to vector. But it refers to a vector only when you are giving information about all the components. Here I am running from 1 to the dimension. So if it is in a three-dimensional space, T1, T2, T3 are given. So it is understood that it actually refers to the vector into the unit vector somehow. This is what actually we have in mind when we talk about the vector. Then Tij, we will have, as I said, will correspond to some element here, and we have tensor product Tj summation over H. As I said, this refers to two things. If I am looking at the context of, let's say, magnetism, it will be something like this. Let's try it. Magnetic polarization is given by an expression like this. This you are familiar? Magnetic polarization. So this is the magnetic susceptibility, the direction of the, this is the applied magnetic field. So this refers to direction of magnetic field and this refers to the direction of magnetization. So they are referred to two distinctly different types of considerations. So corresponding to this one, I will have, so I will say this quantity will be independent of the coordinate system that we use. This quantity will be independent of the coordinate system. But if you look at the components themselves, they will vary when you change the coordinate system. Likewise, if you look at elasticity, you will have something like this. Sigma ij, some elastic constant Cij KL epsilon. You have found this notation? Stress is equal to strain into elastic constants. Can you see this here? No. You apply a stress on a system. I talked about the stress. When you apply a stress, a strain is produced in the system. Or when you strain the system, a stress will be required to be applied. So what is the stress needed so that a strain epsilon K can be generated? That is given by an object having four indices. Because I told you, stress is having two indices. Strain is also having two indices. You take a surface, that surface can be deformed. The object can be deformed either parallel to that one or perpendicular. So this is on par with sigma. So the coefficient coming here should be having dependence on four indices. So this is an example of a fourth rank test.
So the I and J means the same thing, that is direction of force and normal to surface.
Yes.
And what about K and L, both are directions?
These are also referring to the directions.
What directions?
So you can, for example, let's say you take a change in length. Is the change in length along the direction of that one or perpendicular to it? For example, when you shear an object, you take a surface, it is given rotation. So the deformation occurs perpendicular to that. For example, you have got a factor. Let's say you are just moving. Okay, one surface with it, that is the top surface is moved this way, bottom is moved this way. Let us say. So that you start with an object like this, and let's say let it get deformed to something like this. To talk about the strain here, what we will do is you find out how much is this change in length, and that will be divided by this distance. So that whether you look at the full system or you look at a part of the system or this part of the system, you get the same answer. So this is the shear strain. Whereas if you consider a deformation like this going to something bigger than that. Then you say change in length along the direction of the length of the system. So this is a longitudinal part. So whenever you talk about deformation also, it makes sense to say change in length in the direction divided by the original length, or change in length in the two perpendicular directions divided by the original length. So strain also can be defined in three different ways. Got it?
Well, you write epsilon K, and then K index stands for?
K index stands for choice of the direction which we are considering as the
Reference.
reference. For example,
L is the change.
L is change. L is referring to change.
Direction alone is the change.
In general, I can say, very generally, like, this is the direction of the stimulus, and this is the direction of the response. Strain is also one such quantity. You apply a force in a certain direction, then find out how much is the change in that. So generally, one can think of that way also.
So that K and L, I can say L is force and K is.
No, not in that sense. Not in that sense. Here, what I am trying to say is, you take this particular object. It had originally a certain shape. This shape has changed. Now you want to find out how much is the change in shape of the system in quantitative terms, in specific terms. So let's say you choose to look at this particular dimension, or the object along this particular direction here. So let's say that direction is 1. Now we can ask, okay, compared to the original length in this direction, how much is the new length that has come along the same direction? That change in length divided by this original length will tell you epsilon 1. You can find out, keeping this one, how much is the change in length along this direction. That divided by this length, that will give you epsilon 1. Then you can find out this length, okay, as a reference, and find out how much is the change in this direction divided by this length. That will give you epsilon 1. So you can choose the direction of the reference and then find out what are the changes. The changes in the 3 mutually perpendicular directions. Take the ratio of changes in the mutually perpendicular directions by the length in that particular direction. This, of course, you can do in 3 different ways. So that's the way to understand. So the whole part I'm trying to say is that, so physics will be, you will encounter so many such contexts where you find objects which need to be represented by more than one.
So here, what are the bases of this? In the case of CIJK.
So here you can think of this CIJKL, real tensor EJ, tensor EK, tensor. Yeah, I think IJ. That will be the object which will be unknown.
It's an
81. Yeah, 3 into 3 into 3 into 3, 81 elements. But we will not go more into that, but let me illustrate this a little bit. Okay, let's say with the example of.
In this way, sir, any tensor can be considered as the generalization of the vector.
Yes. In fact, this you can remember to the rest of the lifetime. Tensor is a vector. A tensor is a vector in the tensor product space. That is the most condensed way of telling what a tensor is. But let me illustrate this idea better. See, we had this quantity I alpha beta, and then we say omega b. And then we had omega summed over alpha and beta. This is what was there in the context of kinetic energy of the rigid ball. I said this can be now viewed in the following way. I consider first this object. This dotted with, let's say, this is one object that we have. And I'm taking dot product of this one with, let's say, and I'm taking a dot product of this one with this one. Supposing this is still not the final one, but I'm just trying to motivate. Just think of the following. This one corresponds to a vector which represents the angular frequency multiplied by the direction of the rotation. That is the axis of rotation, right? We have said it repeatedly. The vector omega corresponds to the magnitude omega multiplied by the direction of the axis of rotation. So this is one vector. Same vector. I've used different indices to label them because this, whatever the label that we have used here, is a dummy index. Omega 1, E1, etc. This is what it represents. Now I want to talk about making a dot product of this one. So here the way I have written is, this object has got dependence on two vectors simultaneously. The first referring to, as I said, one of the directions, and this corresponds to the other direction of the system. When we take dot product, this anyway, when you take the dot product from there, it is supposed to act on the vector coming as the second part of it. And this vector here is supposed to act on the vector coming here. Got it? So in that case, we can say this corresponds to many indices, alpha and alpha prime, beta and beta. All of them are indices. Omega alpha is a constant, I will write it like this. These are numbers, I will write it like that. And here also there is an omega beta. And then you have got E alpha dotted with E alpha. And then you have got E beta prime. This will give you a delta alpha prime and this will give you a delta. So that means of the sums here, alpha prime should be equal to alpha and beta prime should be equal to beta. So you get omega alpha, I alpha beta, omega beta, something like that. So this is exactly like taking dot products of vectors. But there are two ways in which you can take the dot product. Dot product with respect to the first space, and this is with respect to the second copy of the space. Get what I'm saying? When I put some vector on this side and say put a dot product, that vector dot product has to be done with the first component of this tensor product space. And when I put a dot product from the right here, we have to take the dot product with the vector sitting on this. Got it? That is not very elegant, but that's what it used to be historically. This is what is used to be called the diagram.
That tensor product single should also be coming the second step.
Exactly. So that's why I said this is not the most precise way of writing it. The precise way of writing would be in such context would be like this. You put it as omega alpha, E alpha, tensor 1 here, dotted with, here you put it as 1 tensor. Now you don't have to tell anything, it becomes immediately obvious, because if you have something like, let's say, E alpha tensor E beta, suppose you have to take dot product with, let's say, E gamma tensor E delta. The rule of the multiplication is this part refers to one space. This part also refers to the same space. So dot product has to be taken between these two. And similarly, this part refers to the second component of the tensor product space. So this dot product should be with that one. So the place which has to act with what is immediately made clear when you put it on this one. This stands for basically E alpha dotted with E alpha multiplied by E beta dotted with.
This is a ruling tensor.
This is a ruling tensor. I'm saying this rule is to be anticipated because we are referring to that. Okay. See, this space is actually not general enough to understand that. I can think of something like this. Let A and B be two vector spaces. Let's say of dimensionality, some n. They can be very different from each other, also, two distinctly different contexts. Now, if I got a vector, let's say A belonging to B, this means this vector A can be written as some summation over AI and some EI, I running from 1 to 1. Correct? So, such vectors make the vector space. I can have a vector space B. I said this could be different from that one. That means the vector B will be of the form some j equal to 1 to m, bj into some other basis vectors. Not that one. This can be an entirely different space. Getting what I'm saying? So I can have two distinctly different quantities. Like for example, I am applying an electric field to a system. This may refer to that one. I may have some other field that I am applying that's very different from this one. So I can have distinctly different vector spaces there. Get what I'm saying? Another simple example would be like, let's say this refers to position, this refers to momentum. In that case, of course, the dimension will be identical. But these are two different objects, right? You got the configuration space and the momentum space. So this can refer to, yeah, I think that's a good example. Okay, so think of the problem of doing mechanics in phase space. So you need one set of vectors to represent your coordinates, the position, and another set of vectors to represent the momentum. In that case, M and M are equal. But you will agree that the basis vector here and here are different, they are corresponding to different things. Or let's say angular momentum and spin, that are different things. So you can have objects which are described by or in which the physical phenomenon that you are going to study are influenced by very many quantities of vectorial character. And you want to have a description involving all of them simultaneously. So I can put it like this. The vector space A is of this particular form. You want to write it mathematically, write it like A equal to summation over AI. So that is the description of the vector space A. And my description of vector space will be I equal to n here. And B is, the elements are B and each B is equal to AI. So this is our description of the two vector spaces. Okay. Now I can have the product space, the tensor product space. So I will define it in this way, A tensor B. So these are vectors of the form A tensor. So these are of the form basically AI bj, EI tensor, some power. So the first part of it refers to the first vector space and the other part corresponds to the second vector space. Clear? So if we have got an n-dimensional and m-dimensional vector space here, the tensor product space is n-m dimension space. That is also a vector space. That is the point I am trying to make. So this is a vector space. Of dimension n. We don't normally write it, but whenever we are talking about even systems involving more than one particles, then also we should be using this one. We'll take it for granted. We don't write it. Strictly speaking, we have to do it. And why we can do such things without getting trapped of these mathematical niceties is also a very interesting question. So people who study algebraic structures will be looking at all these problems. But let it be at this level, so I will stop it there. So the correct representation then all of you understand is this one. So this means the other part is like a scale.
You are mentioning these things to show how do we take the dot product between two tensor products.
That is one of the issues. So how to take the dot product becomes evident Once I say that in this one, the omega alpha into E alpha into 1 is the basis. E alpha into 1 means E alpha itself is the basis.
So you are treating a vector space as tensor product between vector space and plane space.
Scalar. Now this is important if you want to understand the transformation. So let's say, as I said here, let me remind you 1 second, V I T here, I equal to 1 to, in this case, let's say, except that this is an invariant quantity. Now let us say we go from this set of basis vectors EI to another set of basis vectors E prime. We do a coordinate transformation. Such that let's say the new basis vectors are of the form matrix times Vij. We are still talking about the vector space going to itself. What all we are doing here is a change of coordinate system. Let's say, for example, when you do a rotation, what do you do? Inverse reflection. The base, some or all of the basis vectors might be getting changed. But because we are referring to the same vector space, the new vector, the transformed quantity also can be represented as a linear combination of the original ones. That is ideal. So in that case, you have to see that this quantity has to be made invariant. How is it possible? If the vector is invariant, if the basis vectors are changed here, then this also has to be changed. So if you write it in this particular form, it should be evident that V prime I, so Vi into Ei is sum. This must be equal to summation over I, V prime of I into E prime. Correct? That's what is required. Which means V prime of I should transform in a manner opposite to that of A here. Another way of writing would be like this. If the basis vectors E1 to En and the components are, let's say, V1 to Vn written in this form. If you multiply this which have the left, let's say, by a matrix A here, this should be multiplied by, because here we can insert A. Still the answer will be the same. So if you refer to E1 to En, this multiplied by this matrix A as E prime 1 to E prime n, the new basis vector, then of course we can say that the E prime 1 to B prime n, this is given by A acting from this side. Is that it? This one, if you look at this, E1 V1 plus E2 V2 etc. E and V, that's what the vector V is. So think of new basis vectors in this particular way. The new basis vectors E prime 1, E prime 2 etc. E prime n is given by this one. Then you get this. Okay? So that is a simple way of understanding how the components of a vector must change when the basis vectors are changed. So basis vectors transform in one way, we call it the components of the vector transform in the opposite. Yes? Is that clear? So that means if I have got a tensor of this particular form, Vij, these are the components of the tensor. Okay? Upon transformation, this will go to some P prime Ij. And this P prime Ij will be given by simply some A and K, Aj and Tj. Sum power of the scale. So if I say Vj, V prime of, let's say, I is equal to summation over Aij and Ik Bk sum over K. That's what this relation will satisfy. If it is written in this particular form, corresponding to the other index also, the transformation should be exactly the same. Because both the components are of equal fitting. whatever be the way in which the first index changes, the same way the second index will also change. Am I going too fast? Are you getting what I'm saying? Because the idea is to communicate. Are you following what I'm saying?